Right, well, thanks for coming, everybody. I'm Stephen. I work as a data scientist at Ravelin. And what I'm going to be talking about today is building intelligent data products. So that kind of means where the product is the data that you collect and the decisions that you make from it. So these are the questions that I'm going to try and answer during the slides. And then we'll go on to talking about how to build these kind of products. And then some heuristics to think about when you are building these. So a bit about me. My name's Stephen. I spent the 2 years previous to this working at Hailo. I was a data scientist there, jack of some trades, primarily doing a bunch of analysis-based stuff, so kind of traditional data science research. I also did some engineering, the quality of which is kind of very debatable. But I built some stuff around stream processing. So, for example, I built a service that captured all of our GPS data and then allowed you to query it and see the speeds of various drivers in London. And that factored into our traffic estimation times. What I'm doing now is I am a data scientist at Ravelin. So I'm primarily focused on the detection capabilities of our product. So essentially trying to catch fraudsters as quickly as possible and as accurately as possible. So what on earth is Ravelin? So it's an online fraud detection and prevention platform. So you can think of it as you have some application that takes credit cards, and then you stream application data to us in real time. We will then give you a score back, in around 200 milliseconds that tells you the probability that this customer is likely to give a chargeback to you. So essentially, they've stolen the credit card, they pay for something, and then someone 2 months later will go and say, hey, that wasn't me. We do this as fast as possible, and we also give a nice data visualization so you can understand more about your customers and the behavior of fraudsters kind of versus genuine people. So we talk about fraud, but what actually is it? So the scale of it is massive. I'm sure that pretty much all of you in here have been affected by someone stealing your credit card at some point during your life. There was $14 billion lost in card-not-present fraud. So that's when you take an Uber or a Hailo or any of these services and you don't actually have the card physically there to make the transaction. So this is, eBay, Amazon, all of these style services. It's $1 for every year the universe has existed, depending on which view you take. So if you think about it, the time to delivery for whatever you're doing, if you're a greengrocers to kind of just a traditional retailer, the time to delivery is getting shorter and shorter. So if you think about Argos, they used to be, you go to Argos, you go and wait at the till, and in 20 minutes it would arrive to you. But now they've partnered up, I think they've partnered up with Shuttle, and you can get your thing, whatever it is you ordered, in less than an hour. So instead of having this kind of time where traditional retailers could say, here's an order, we'll take a couple of days to look into it and see if it looks genuine and then ship the goods. You kind of just have to ship the goods straight away. If you think about Amazon Prime, you can get basically anything delivered to you in less than an hour. And then there's a real spring of on-demand startups like Uber, Hailo, Deliveroo, etc., that have basically no lead time to make a decision about whether something is fraudulent or not. Because if you think about Deliveroo, they have to pass the order to the restaurant as soon as possible so they can start cooking the goods. And they can't really cancel the order after the goods have been cooked. They have to make a decision pretty much instantly. And the police are not great at handling this problem. They're kind of, I guess they haven't caught up with the technology behind it, so it's kind of perceived as a victimless crime because in most cases the only victim in this situation is the merchant. So the person that you actually bought the stuff off of, they have to bear the cost of what was spent. There's a ridiculously low barrier to entry to stealing one of these credit cards. So if you just jump on Tor and go kind of searching in the murky parts of the web, you'll be able to find a bunch of credit cards available with a money-back guarantee, believe it or not. And you can 3D secure. I'm sure you've all seen this abomination on a mobile screen. This is proven to be a conversion killer for a lot of mobile startups because this on a mobile screen is terrible, and most of it involves asking convoluted questions that you don't really even remember the answer to. So a lot of the time people just say, screw this, I'm not carrying on. But the thing about this is that if you choose to do 3D secure, then the liability of fraud it's basically transferred from you. So you don't have to pay the fraud, but often the cost of the fraud is lower than the drop in conversion that you get from using this. So how did we used to detect fraud? So traditionally, we used to impart our knowledge about what fraudsters look like, and we'd create a bunch of kind of rules, decision tree, and then we'd just iterate through those things. This takes a very order-centric view of the world, so it thinks about, what is the person buying, what is the payment method being used, but critically, it doesn't stop the customer before they even get to that point. What we try and do is we try and augment this kind of human domain knowledge with kind of large-scale machine learning, and our goal is to stop the customer before they even get to ordering with your application. And we think that it's not orders that are fraudulent or cards, it's actually the customers behind those things that are the fraudulent parts. So we try and agglomerate all of these things together and then think about them in terms of customers as opposed to cards or orders. So this is a slide that might kind of cause you some visual damage. So there's an N amongst all of these many M's. You might have seen it, don't shout it out if you have. This kind of illustrates the problem that we face at Ravelin, is that fraudsters are extremely rare, but when they do happen, they have a disproportionate impact on the application. So if you think about this, there's 999 M's here and one N. If you didn't see it, I think it's right there. So yeah, this illustrates, there's just one person here, and they're kind of hanging around doing some fraud. But when it comes down to the actual impact on your margin, it can be huge. Let's say you make 5% on every order, but you have to guarantee the payment of the whole order in every case. You can then see that you'll be having to pay out a huge amount of money if you just have one order that is not good and you have to pay out at the end of it. So this is essentially the problem that we're trying to solve at Ravelin. We want to protect you from that big kind of evil N having a problem on your end margin. So these are a couple of heuristics that I've picked up over the past years when kind of building data products. So if you have some kind of statistical model, you can basically kind of train it to optimize for a few different variables. And you have to realize that the customers that you're selling your product to, they essentially care about different things. So a really good example of this is like a growth stage startup versus a very kind of old, an older business that's focused on just protecting margins. So if you're a growth stage startup and you have a high cost of acquisition of a customer, you actually probably really care quite a lot about false positives because you just want to grow as fast as you possibly can, and you want to make sure that all customers have a great experience using your product. And you can probably eat a small amount of fraud if you've kind of raised a decent amount of money and you're growing faster than the fraud is. If you are a kind of more mature business, then you probably care about the other side of it. You care about this kind of, I'd rather catch more fraudsters at the expense of some false positives. So this is something you have to think about when building these data products. Essentially, it's a sad trade-off. You can spot a lot of fraudsters. You won't spot all of them with no false positives. So you have to think about what are the metrics that I care about when building these data products, and make sure that you build models or ways to affect your models that can deal with that. So this is thinking about, there's a few metrics here that are interesting when building the systems that we build. So there's precision. So of all the predictions, of all of the people that I said were fraudsters, what percentage was I correct? That's different to recall very slightly into of all the fraudsters that were in the world, what percentage did I catch? So if you have a very high recall but a very low precision, you're essentially just saying, I think a lot of people are fraudsters, and the likelihood you'd catch most of them, but the likelihood that when you said someone was a fraudster, they actually were, would be quite low. And this is what I was illustrating in my previous point, is that if you are kind of a growth stage startup, you probably care more about precision. And if you're a kind of an older margin protecting one, you care about recall. So accuracy is also a very useless metric for fraud because you're dealing with ridiculously imbalanced data sets. So 999 good people and 1 bad people. So this is a model that we've been working on, and it achieves a very high level of accuracy. So yeah, you can basically say, no, you're not a fraudster, and you'll be right 99.91% of the time, which illustrates that you should choose a good metric, and you should optimize for that. So this is a kind of talk about the tooling that we use, and how you should basically choose to buy tools that make you disproportionately productive. I know that sounds tautological and obvious, but we have been kind of really big fans of BigQuery. So we stream all of our data into it in real time. It's a SQL-based append-only data store, and you can just essentially write all the crap you could ever want, and you just be able to query it instantly, and it will go over terabytes of data very quickly. So we use this both for analysis and also for the infrastructure side of stuff. So all of our application logs are streamed directly into BigQuery. All of our traces. So if you think about services talking to each other within our infrastructure, every single one of those is streamed to BigQuery as well. And then we just run a little daemon on every box that streams all this data in real time. So I couldn't recommend it enough. Please come chat to me later if you think you have a use case and you want to talk it over. So our analysis stack, it's me and Relly as a two-man team. I don't know where Relly is. There it is, in the green jumper. So we use a mixture of BigQuery, Jupyter Hub, which is the IPython multi-tenant kind of notebook solution, Pandas, and scikit-learn. And this powers our analysis toolset. And it basically means we don't really have to care about any of the infrastructure things, about like running data warehouses or running servers to deal with all this stuff. We essentially just use the Google network that ships data around super quickly internally. So if you're even pulling data down from Google Cloud Storage, it's extremely fast, and you don't have to really kind of sit around and wait for large amounts of data to be shipped between places. This is another heuristic, which is kind of saying, just keep your model interfaces really simple. So we have a model server inside our infrastructure that essentially you just have to have three methods. Three methods to be called a model. Just an ID, which is a string, score, which is a feature, and then returns a probability and an error, and then a bunch of string explanations about why you made the decision you did. So if you think about that, you can then hide kind of arbitrarily complex things behind that interface. So let's say I have a bunch of imputation that I need to do on some data, or I need to transform it in some way. As long as you can bake that into stuff that's behind that interface, then it means that you can iterate very quickly because you don't have to be writing custom code for every model you ship. It's really good to version control them as well. Just treat them like normal code. So we can roll back, roll forwards on all of our models. And it just means it's a lot easier to test stuff, and you can roll back in history and score against a data set to see how it was performing. And then this is a heuristic that I'm kind of pretty behind. If someone's neck is on the line for a decision that your model made, you should probably allow them to understand how you came to that decision. So let's take the example of a fraud analyst that's going through all of the orders that have happened, and let's say Ravelin has flagged it up as being highly fraudulent. And let's say, in the obviously very rare case that we get things wrong, you want him or her to be able to explain to their boss why Ravelin thought that, as opposed to just saying, computer said, no, it was true. You want them to actually be able to explain that and understand, and then via that explanation, feed their own knowledge in about why you were incorrect in that decision. I don't think it's really acceptable to just provide black box scores in these situations. And then kind of people say, oh, well, you're going to be trading off performance in this case. You won't be spotting as many fraudsters. And I think that what we're using right now, so we're using random forests to detect fraudsters, and you can actually introspect the trees in the forests and give some kind of explanation of what's going on internally. So they provide quite a nice balance between explainability and performance. It's not this kind of linear scale that everyone talks about, but the easiest way to determine where you lie on this scale is train a logistic regression on some data, and then train a deep neural net, and then compare the performances of the two of them. And if the difference is marginal, then you should probably just always go for the logistic regression, because you can explain it. It's a lot easier to understand why it's going wrong. And then you'll be able to provide kind of feedback as to why you made the decision you could. So this is talking about the random forest, which has now been set on fire. So this is about monitoring and figuring out when things are going wrong in your machine learning infrastructure. So there was a paper published a couple of months ago called Machine Learning, the High Interest Credit Card of Technical Debt. And I think this is, in my very short experience of it, it's kind of true, because there's so many ways that things could potentially break when building machine learning infrastructure. So you have, data leak between your training and your test set. You have time-based data leaks where you need to cut off at a certain time and, train on one set of it and then test on the later set of stuff. Imputation going wrong, scaling going wrong. So you always need to be monitoring this stuff and probing for edge cases in it. So the way that we do it is we kind of dog food. We use robot customers that essentially sign up, send events through our API that look variously good or variously bad. And if we don't score them with an accurate, if we don't score the right end of the scale that we would like to, then something is obviously going wrong. And we kind of get notified on Slack about that. So you can also run strategies in dark mode, so you don't actually send the score back straight away, but you instead just log it somewhere, and then you can kind of iteratively build up whether this is more and more accurate, and then switch over to it. In time, we'll probably build something that kind of automatically balances between our various predictors to always send the most accurate score. So yeah, it's basically the kind of heuristic behind this is just be massively paranoid about everything that could go wrong. I don't actually have a timer on my screen, so I don't know how long I've been. Lenny, how long?
You got about 5 minutes left.
Cool. So I can now do a 5-minute pitch about Ravelin. No, I won't do that, don't worry. So we're in beta and signing up clients. We essentially just want to work with people that are facing fraud problems so we can perfect the product and just kind of build off the feedback that we'll get from you. So we're looking for on-demand services and marketplaces and PSPs, people that process credit cards that are facing fraud problems. We'd love to talk to you and kind of figure out how we can help. Just come and talk to me afterwards. And then next one in series of annoying slides, we are hiring. So if anyone is a junior data scientist that would love to come and work on interesting fraud problems, then please give me a shout and talk to me afterwards. And we can take it from there. And thanks very much.
Does anyone have any questions for Stephen? Not one? Come on, you can do it.
Go for it.
Okay, let me give you this.
You mentioned this trade-off between the, some capabilities of, let's say, if you have logistic regression and machine learning. Tell us a little bit more about how far you can get things with logistic regressions in which cases, because that's one of the dangers, right? That when you have a lot of computation, sometimes you won't be able to explain things. So
yeah. So the question was kind of explain more about the trade-offs you make between using more simple models and using more complex models. So I'm kind of speaking from ignorance here. I've never really applied kind of deep learning methods, and they've largely been very successful on more complex problems like speech recognition, translation, etc. I think the position I'm coming from in Ravelin is that if we were going to trade off between performance and explainability, right now we'd probably always choose a bit more on the explainability side, because I think it just builds a kind of much better product. If you have these highly complex problems, so let's say there's a Skype product that will translate your speech in one language to speech into another language. So that's not really something you could do with the logistic regression. Using deep learning, these kind of arbitrarily complex transformations are a lot easier. Sorry, not easier, but are a lot more possible with these things. But I imagine they're also extremely hard to debug. So I would say that I don't have much experience with the highly complex models, but from my perspective, it's a lot easier to figure out when someone that is obviously good, a genuine customer is being scored highly. you kind of want to know, okay, what is the real key thing that is behind that? And I feel if you use very complex models, that becomes a very hard problem to solve. Thanks.
There's another guy at the microphone. My lovely assistant.
Hello. Just wondering, what are you using for features, and how big is that feature set?
So we currently run, like all of our infrastructure at the moment for running live stuff is on AWS, and we use Postgres for storing kind of all of our entity data currently. So there's a difference between what data do we, how do we train the models versus how do we do it in production. So the production stuff is a service that essentially you give it a customer, and it will go and run a bunch of queries and then do aggregates in memory. So the feature set currently is about 300 or 400 different features. They kind of follow a power law of how useful they tend to be. There's a few things that are extremely kind of useful in a small amount of cases, and then there's the bigger things like how old is the customer, how many cards has the customer added, all of these sorts of things that are extremely useful. So I would say, yeah, we're using Postgres for all of this. We push a lot of the computation from Postgres, like, imagine doing counts and aggregates. We pull it all in internally and do it in memory. And then we do we kind of do that and then ship that onto a queue or to an RPC-based thing where we can make decisions off of that. So yeah, it's about 300 or 400 features at the moment. And it's always growing, much to the back-end engineers' dismay.
Hey, how do you deal in general with sequences of transactions? So basically, if a customer does A, B, C, and then it's a feature for, let's say, for fraud, or a signal for fraud.
You mean like taking specific actions in a sequence?
Yeah.
So,
or behavior, for example, of days, or does it matter? Or?
Yeah. So I think these in the kind of the fraud world are kind of velocity-based things. So they are really predictive of fraud. If someone, the most fraudulent customers essentially sign up with a bunch of cards, try the cards extremely quickly, and then if the cards are good, they will then kind of proceed to just rinse the account for all it's worth. So these velocity-based features of, someone going from nothing to a very high amount very quickly is extremely predictive of fraud. So we capture that in various ways. There's, count of transactions and last minute, hour, all of this sorts of stuff. I'm sure all of you work in, a bunch of you work in tech startups and know how hard it is to get people to install your product and actually use it. Fraudsters tend to look like, the dream customer as well. In a given way, it's like, someone signed up, they're instantly using it, and wow, they're spending hundreds of pounds. So it's this problem where you have to distinguish between those, but the average customer for a startup is probably, unfortunately, a lot lower than them. So it's a good way to kind of split the data is these velocity-based features.
Cool. Any more questions? One last question.
I guess it's a question around the strategy. Is there a sort of a tension between kind of in-house fraud detection teams and sort of fraud detection as a service that you're taking on? Yeah,
so I think kind of I'm kind of guessing here, but I'm guessing that a lot of the kind of larger online retailers that are not more tech focused like Amazon. I assume they have very large internal teams that are spending a lot of time combing over these transactions. I think what Ravelin is aiming to do is kind of aiming to not replace them, but augment them. So they've picked up a lot of domain knowledge about their business and about what fraud looks like. With our product, I think we're trying to not replace that, but instead just capture that and feed that in, and we view that as a strength on our product to do that. So yeah, I think that there definitely is a tension there, but we're more on the side of trying to capture the very valuable expertise that they have.
Cool.
Thanks.
Thanks very much, Stephen.
Thanks, everyone.